Hi, Shwini. Good morning.
Hey, Sumant, how are you?
I'm good.
Good. So what's going on? What are you working on?
I'm catching up Thursdays and Fridays.
Mm-hmm.
Yeah, so
Okay.
it's kind of yeah, good learning curve. So
Okay.
I might ask you for like a quick session on Wednesday if
Sure.
possible, but I'll
Yeah.
work through
Mm-hmm.
it,
Mm-hmm.
and based on my uh, items, I'll reach you out. Um,
Sounds good.
so yeah.
So how about the assignment on the first week? I
Yeah,
haven't seen that.
I haven't honestly, I haven't worked on it.
Okay.
Yeah, I had like a personal commitment, so
Okay.
didn't
Mm-hmm.
much time, but I'm gonna catch up on that as well. Yeah,
Okay. Sounds good. No issues.
yeah, but
As long as
it's
you're
on my
keeping
thing.
up,
Yeah,
yeah. As long as you're keeping up with it, I think that's fine.
okay,
Um, don't
yeah,
don't give up. That's the main goal.
mhm, yeah. I feel there is pretty big learning curve, especially
Mm-hmm.
after what I read through the Thursday and Friday
Mm-hmm.
for me. So it's taking a little longer than expected. Uh,
Mm-hmm.
to uh,
Okay.
yeah.
So
Mhm.
about that, so initially I didn't plan to, I mean, I was not planning a lot to um, make you write the programs. I was thinking like maybe just using AI to do that for the most part.
Mhm.
But then I realized that making you do the stuff like actually gets you gives you more kind of
Yeah,
like
depth.
experience and depth, and
Mhm.
also going to be painful, but maybe that's kind of like a short-lived pain. You
Yeah.
can live through it. So
Oh,
yeah, so
yeah.
don't stress too much on it. Try to see how much you can, and learning is always in layers, right? You never learn um,
One go. Yeah.
one go. So, and the first time, if it doesn't hit it, that's okay. The next time you can come back and try it. And um,
And
the most important thing is recollection. So, um, I mean, I'm reading like material on like how to make things stick and things like that.
mhm.
So one of the main things that they tell you is like, um, we are trained to think that if you're learning and if you want to make the material stick, you just relearn it or go and read it again, right? That's
Okay.
kind of what the method that we have been taught in school. That's the
Mhm.
most prevalent method, but actually that doesn't work.
Okay.
So recollection is what actually works. What I mean by that is like, let's say you learn something and then you want that to stick, you try to recollect it and you feel
Mhm.
crappy because you cannot recollect it, and you feel like dejected, the feeling is kind of like bad, right? Like okay, I'm not able to recollect what's going on. Maybe I'm not reading it properly. So you get all those feelings. But if you just ignore that, um, internally in your head, recollection is the one which strengthens the bonds, or like the connects the synapses that strengthens the knowledge that you gathered.
I,
So
I see. Yeah, one thing
so
I've been
mhm,
experiencing is
mhm,
practice exercise.
mhm,
I'm not able to grasp or try to figure out the question. So
mhm.
that's one other thing I have been spending time. Um,
Okay.
yeah. So
Yeah.
most
So
probably that's where my questions might be. Yeah.
okay. Yeah.
Yeah.
So on that side, I think I would
Mm-hmm.
say that it is kind of, as I said, I mean, I mentioned before, right? It's not like um, I'm trying deliberately not to do hand holding,
Uh-huh.
uh, and trying to see if I can basically jumping certain hoops, right? Like I'm like,
Yeah.
okay, I tell you this, and then on an exercise, I tell you something else that you haven't seen. So now
Mm-hmm.
you cannot just read the material and make sense of it. You might have to connect
Think
the
about it.
dots. Yeah, think about it. Maybe look outside the material and everything. So it is intentional. and
Okay.
that's how we learn. So one other thing I learned in like I mean
Yes.
I already mentioned that I'm working at CMU for more than a
Mm-hmm.
decade now. So before coming here, everything was kind of like handed to me, and like learning was kind of that. And then when I got into CMU, which is one of the best schools in software engineering and robotics, I was like, okay, maybe they'll tell us more, even more, but actually they don't.
Yeah, I experienced same thing
Yeah.
when I started here in
Hmm.
school. So
Hmm.
it was painful, honestly, keeping up
Yeah.
with the amount of like learning how we have to think and deliver. So yeah,
Yeah.
I feel
So the
similarity in terms of assignment or
exactly.
yeah,
Yeah.
but at that time, I might not had patience, but over the
Hmm.
years, I
Hmm.
feel you have to go back, keep pushing,
Yeah.
and
Yeah.
yeah.
Yeah, the goal is not, I mean, when I joined CMU as a grad student,
Mm-hmm.
I had the same feeling. I was like not doing things, and I was like also frustrated. Like I was a star in my school, but then when I came here, like there are so many stars, like I was no
Yeah.
one, and so it was kind of like hard. And I was like, okay, why am I not able to do these things? And it's always the grades and everything, but as time goes on, you kind of figure out like, okay, it's not the grades, it's none of those things, not the exams, anything. It's all like, okay, do you learn it or not? That's all matters, right? So just keep up with that, and then you
Yeah.
should be able to.
I struggle pretty hard with the grades as well. So
Yeah,
yeah.
I guess like people from like if you're from India, then it's the education system is a little different there, right? So it's kind of like hard here.
That's what I have been doing in a
Okay,
sense.
sounds
I
good.
am trying to, yeah, practice exercises where I'm like missing out to
Mm-hmm.
develop the answers. So
Mm-hmm.
my focus, like next few days, would be just
Mm-hmm.
catching up on those, and I'll reach out based on where I get stuck.
Okay,
So
sounds good. I guess the you probably got the assignment for this week on like today. It's going to
oh,
be much more
okay,
harder. It's a
okay,
little bit more harder, so I'm just warning you upfront, but
hmm,
that's okay. Just
yeah.
keep at it.
Um, uh, Hi,
Yeah,
Krishna and yeah, Jishnu.
yeah.
Yeah.
Hey Krishna, Jishnu, how are you guys doing?
Hi, sir. Good.
Good, good.
Hey,
So
I'm also doing good.
good. So are you guys like ready for Diwali? I guess that's 2 days now, right? Like I don't know. You guys
Monday.
are like yeah. So this today is like Saturday night for you guys, I guess. So
Yeah, the Diwali is on Monday.
yeah, yeah, okay, okay. Do they have do you guys like travel somewhere or like I know some people go to their hometown during Diwali.
See the family. Yeah.
Yeah, yeah. I when I was a kid, I used to go to my father's hometown, like a village. It was like during Pongal.
Hmm.
Every year we used to go there. I mean, everything has changed now. Like I mean, villages are no longer villages. So
Yeah.
yeah. Okay, so what's going on? Jishnu, I know you're let's get back to your accountability thing. Have you been doing some stuff?
Actually, past 2 weeks, I wasn't able to do much in the sense I
Okay.
was totally focusing on the work.
Mm-hmm.
Uh, it was pretty tough schedules, so
Mm-hmm.
I couldn't manage with what I actually planned to do.
I see. Okay.
So,
Well,
so this
don't
week
give
I'm
up.
planning to get back.
Okay. Sounds good. So is that like do you get like 1 day leave or like for Diwali or is it like a couple of days?
No, I actually don't have any leave for Diwali.
Oh,
It's
that's
going to be a
terrible.
working day.
Hmm. Isn't that like a national holiday there?
Uh, I don't think so, but my company is follows the US calendar.
Oh God, that's crazy. Okay. Yeah, no, I guess like you guys are working here, but then you guys are working there, but still as like following the US calendar. That's terrible. Well,
Yeah.
anyway, good luck with that. Cool. How about you, Krishna?
I actually I took time for downloading ROS, Gazebo, and Arviz, and I did some like basic node setups.
Mm-hmm.
And I have ordered some items and like Arduino kit, and they will reach on Tuesday.
Nice. Okay.
Yeah, that's what I did.
Okay,
That's all
cool.
I did.
That's good. That's good. Yeah, I think any progress is better than no progress at all. So, cool. So, okay, I didn't have anything prepared for the meeting today. I was just like going to join and like based if you have any questions, I'm going to answer that and then log off. So, do you guys have any questions? Do you want me to talk about something?
I'm curious about bipedal robots. So,
Bipedal robots. Okay, like a humanoid?
yes, like how they manage the gait of walking and all those things.
I see. Okay, well, I'm not an expert there. I can tell you things that I kind of know about. Um, I think Sumant, you were asking something. Uh, did you have a
Oh
question?
no, I was just saying. Uh, I mean, uh, just basics of Git.
Mm-hmm.
That's one thing. Yeah.
Okay.
After once we
Okay.
finish the other topics, yeah.
Okay. Sounds good. Jishnu, did you have something?
No, I thought of catching up with everyone. That was my
Sounds good.
plan. So
Sounds good. That's better. I mean, I guess I did tell you like, okay, doing something is better than nothing, but even more important is like showing up. So that's good. Good that you're showing up to this and make sure that you're asked for your accountability and you can answer that. So that's good. Okay, so on humanoids, what do I know? So on a high level, you could think of humanoids as um, similar to a robot arm, where you have these multiple joints, and then these joints are connected in a certain way, and then you try to do manipulation. So when I say a robot arm, what I really mean is in a robot arm, you have the base fixed. So you kind of expect that there is not going to be a lot of torque at the or you're going to nullify all the torque that you exert in all the other parts of the arm. So so the balance is a little easier there compared to when you have a humanoid where, let's say you just lift one of the arms in the humanoid, then your center of balance is kind of affected. What I mean by that is when you, I see Aravind joining as well. Okay, so what I mean by that is like when you're changing some part of your body, like lifting your arm or extending your arm, having a weight at the end of the arm, the center of gravity of the whole robot kind of shifts. And in a robot arm, you care about that to some extent, but there isn't much you can do. Uh, you just expect that the base is fixed to a fixed frame. Whereas in a humanoid, you'll have to balance your other parts of the body. So, for example, that might mean raising the other arm or raising a leg or maybe shifting the hip in a certain way so that the center of gravity is still aligned, which is kind of something that we all of us do naturally, but for a robot you have to do that. So there is this thing called this whole body control algorithms. That's what they use, and that tells us like that tells the robot like, okay, how they have to switch the position or like how they have to shift to account for the weight. So this kind of becomes a much more complex problem, because even a slight off in the balance, it would cause the robot to just tip off and fall. And on a robot like that, falling off is something that you definitely don't want to happen, right? Either both due to reasons like hardware costs and things like that, that you'll have to go through to repair that. But also, like, when you think of a robot like a humanoid, you expect it to be balanced, right? Like, you expect it to at least stand without falling off, even if someone is not pushing it or something like that. So when you have adversarial conditions, like someone pushing the robot or something tipping the robot, then it has to react even faster and kind of like account for that forces that comes in. So things like these whole body control, and then also the higher reaction times, are kind of like crucial for a humanoid robot to survive. There is also other thing which is important, in the sense that the torque of the motors. This is something that we generally don't think of. It's like, okay, why would that matter for a humanoid? So if you're trying to if you're getting some adverse force, like something that is throwing you off balance, you need to react as fast as possible to account for or counter that force, so that you don't fall off. And the faster you can react, the lesser the lesser the amount of force is needed. But then there is going to be a fixed amount of time that is needed for um, to do the processing and calculate how much you need. So there is going to be a set delay. Maybe this could be like a couple of milliseconds. If when then you have to account for that, and which means that you need to have higher torque to account for that. So the way to think about it is like, let's say you're falling off, and let's say you just stand with one leg, and if your balance is off and you tend to fall off, you can adjust your position with a little amount of effort. But when you're almost falling, like you gone past a certain stage, you need a lot more force to pull yourself back and get it back in position. So for these humanoids, then what that means is, like, you need to have a lot of torque that you can exert on the motors to recover from these falls. So that is also another consideration when they do these humanoids. And you would have seen a lot of robots doing these front flips, side flips, back flip, and all those things. The reason why these are impressive, I mean, it's a good eye candy thing. Like, you can watch it and you're like, yeah, this looks cool. But more than that, it is kind of like it stresses the system to the maximum extent, because now you need to have these reaction forces calculated at a very fast pace, but also have the motors capable of providing the torque to kind of upright yourself and stand. So that's kind of like the um, what makes humanoids harder. And that's one of the reasons why humanoids have not been in existence for so long, right? Like, we've read about this in science fiction for so many years, but the one robot that was kind of like worked upon is that I remember is, it's called the Asimo from Honda. This was like, I've looked at, yeah, the first time I joined CMU, this was in 2008, is when we actually saw like we had like a robot there in the lab, and I was just saw that in person first time. And Asimo has been in existence even before that, like in I think from 1990s is when they were building that. And then Boston Dynamics built it, and but if you look at those robots, none of them were electrical. All of them were hydraulic based. um, the main reason was because um, we didn't have sufficient, like, the motor technology was not progressed, has not progressed enough that to provide that level of torque, and also the control algorithms. Well, even for hydraulics, you need good control algorithms, but then the motors is one of the main reasons there. So now that the motor technology has progressed so much, I mean, mainly due to drone technology, like um, like if you've learned about motors, there are multiple types, but the two common types is like brushless motor and a brushed DC motor, right? So the brushed motor is what we much familiar with. That's what we have tinkered with in our schools and things like that. But a brushless motor is a little advanced than that, and having control systems for that is a little bit more involved. The drone technology pushed the brushless motor technology to such a great extent that we can get really tiny motors with a lot of torque in them. So we can employ that in these robots. So I think like maybe 5-7 years ago, Boston Dynamics switched from their hydraulic based robot to a electric robot, and now like almost all the humanoids are electrical based. Like none of them are hydraulic based, primarily because hydraulics, like dealing with hydraulics, is painful. Like there's a lot of things involved in that. Like it gets messy. You could have oil leaking somewhere, and I can get into your electronics and maintaining that. It's like if you think about it, it's like difference between maintaining car which is run with gasoline versus a car that is run electrically. So like a Tesla car. A Tesla car is a lot more simple mechanically than an engine car, like a car that uses gasoline, right? Like you have the number of the part count itself is an order of magnitude lesser. So an electric car, let's say if it has like 10,000 parts, and a gasoline car would have like 100,000 parts. It's like that complicated. You have this piston, you have this spark plug, you have this thing, and then within the spark plug there are like 10 parts. So it is pretty complex. So having hydraulic based drive system is kind of pain. So that's why all of them are moving away to electric base, which is much more easier to maintain. So that's one part of it. And then why were the humanoids not doing flips before? Because of the control system. Like computing has progressed so much that you can now develop these algorithms which can run in like fractions of a second, like millisecond control loops, whereas in the past you cannot do that. And so that was another reason why these robots are like we're not doing flips like maybe 10 years or 15 years ago. Sumant is asking, can you explain what is the algorithm?
I mean, I don't
how-
know what shape or like form we write the algorithm when you say algorithm.
Oh, I see.
So yeah, and
Mhm,
then how like it differs from a code or whatever we call it or make
mhm,
it work.
mhm.
So
Yeah, so when I say algorithm, what I'm talking about is basically a series of steps, right? You're just telling in like in plain language, or you could use some kind of notations for algorithms. But essentially, you're just saying that it's kind of like for humans saying that, okay, these are the steps that this thing has to do. And But you cannot just feed an algorithm to a robot or computer. You have to write it in a programming language that the robot understands. So it's
mhm.
either Python or C++ or C or something. It could also be something like if you're using MATLAB and Simulink and things like that, then you can use those kind of programs. What essentially those do is like you kind of set up the algorithm in a visual environment, like a control setup, like a control loop, like blocks and connections, and then it automatically generates code in the background, and then that's what is deployed. So essentially a robot can just understand code, in fact just assembly language. But then what we do is like, okay, from the assembly language we have these abstraction, which is these programming languages, and then from this programming languages we have these another abstraction where if you're doing block diagrams, then something generates code from block diagrams to either assembly or the programming language that the robot can understand. So,
Okay.
yeah, I think Arvind has a good point about the control algorithms. Arvind, do you want to unmute and talk about it?
Sure, sir. So, are you able to hear me well?
Yeah.
Okay. So, when it comes to control algorithms, there are two basic ideologies. One was classical based approaches, which have been there for a very long time. I guess Asimov was built based around it. So, even inside classical approaches, there are two main methods, using kinematics and using dynamics. So, the simplest method, in my opinion, is kinematics based. just manipulating angles and having a closed or open loop system based on just the angles. A little bit
see.
more advanced when it comes is torque control, which gives you a whole lot more dexterity and robustness with respect to what you can do. But this requires a lot more complexity, both in your calculations as well as your actuators. So this is again a classical method, but this only works in a well-defined environment. When it comes to rugged terrain, it becomes a little bit more difficult to build dynamics-based algorithms. And finally, what we can see right now is reinforcement learning algorithms, which are extremely robust for all kinds of different environments. So these are being built in much more prominence right now because of the increase in computing power that we can see, especially due to the presence of GPUs that can help you with a lot of calculations at the same time.
Okay. Yeah.
Yep, that's
Thank you.
cool.
Mhm.
So I think to add on that, we did talk about dynamics and kinematics like probably last week or like maybe a couple of weeks ago. Can someone tell me like what is the difference? Like what's the difference? Like what gets added in dynamics? Any thoughts?
Inertia.
Yeah. Basically, you bring in mass, right? Like you say that okay, this object weighs this much, and then that with that comes momentum and inertia and everything. So kinematics is basically well, geometry is just like angles and distances, right? So when
Yeah.
you talk about geometry, you're just saying that okay, this object is this far from here, and then maybe if you have this elevation, then or you have this arm and this angle, you basically just say you don't care anything about time or anything like that. It's just like okay, what is statically the relationship between objects at different positions? That's geometry. Kinematics is where you add time to the equation. You say that okay, I care about this position, but also I want to see what it's going to be at a particular point in time, like in maybe 2 seconds from now. So basically, we're throwing a projectile, and then you're saying, okay, at this time, where will that projectile be? So now you need to calculate both the location, but also like depending on the time. So kinematics is including time, and dynamics is basically including the mass of the object as well. So if you're throwing something, and you can just assume like well, if you don't assume any mass, then you can just use kinematics. But then you say that, okay, this is a heavy object, but depending on how much, so if it's a heavy object, you have to throw it with a certain amount of force to make it go beyond a certain distance, right? If it's a lighter object, maybe you just throw it with a lesser amount of force. So that's when like dynamics is basically dealing with that mass in the equation. And then even for the same projectile, depending on the mass, your equations would vary. And as Arvind mentioned, when you as you start including these variables into this equations, it becomes hard to manipulate the equation, right? Like just mathematically, it's hard to calculate the Jacobian and other things that are needed to calculate how things are going to change. So that's why it is like typically if you can deal with kinematics, and if you can like solve the problem with kinematics, you generally go that route. And if it turns out that this is a really heavy object, and or you have other things into play, then you'll have to implement dynamics. So even in robotics, like in at CMU, we generally go with kinematics. I mean, the bottom line is if you can just use geometry and solve the problem, that is the best, right? Like you don't want to add more complication to your solution. But most of the times, or like almost all the time, you cannot just survive with geometry, because you need to have time in the equation, because you're trying to figure out or you're trying to do something, basically change over time. So you need kinematics. But then if you can deal with it without introducing dynamics or mass, then you do that. So an example is like we're working on an algorithm that is basically adapting an algorithm for driving a vehicle in a agriculture farmland. And we've been just doing it with kinematics for that. Like we wrote the kinematics for it, and then we implemented that. It works fine. But then we are dealing with a much more heavier vehicle than that now. And So now we are considering, should the kinematics, will that kinematics be sufficient, or do we need to introduce dynamics into the equation? So we'll first test with the kinematics. If it doesn't work, or if it's deviating too much from our predictions, then we'll start introducing dynamics, which is painful, but we'll have to do that. So that's how these things get determined. And then one other thing that that Arvind mentioned about reinforcement learning. So the two parts that are needed for reinforcement learning is you need to have a lot of data, and you need to also have computing. Um, I could say a lot of computing, but also a specific type of computing. I mean, if you have like a really great processor, a general purpose processor, maybe that will not cut it. You might need some kind of a GPU kind of processor. So what makes these possible is obviously the lot of data that we are getting now, but also the end I think it's called end computing. Basically, these GPU machines, which are tiny, that you can put in any robot. Like NVIDIA is making a lot of these. These are these Jetson modules, which gives you these GPU that can be deployed on like in computers, like any computer that you're have in the field. So so that once you install those computers, then you can actually have the GPU power to run these algorithms, and that's one of the reasons why these are becoming much more relevant. And I think the other part of it is like these algorithms are also getting better, like because of the explosion in the deep learning and all these data-driven methods. All of these algorithms are also becoming better. They used to be like, okay, reinforcement learning, maybe this policy is kind of the common, this is what people do. Now they're figuring out like different things that they can use, different tricks that they can apply to make it better and all those things. So I'm not an expert in reinforcement learning, but I know there's a lot of things happening there. So so those are the two things actually pushing people towards the reinforcement learning thing. One common misconception there is like people think that, oh yeah, classical is hard, maybe we should just use reinforcement learning, because you don't actually deal with the equations, right? Like you just say, okay, feed it some data, make it do stuff, and then it'll just automatically do it. That's kind of a common misconception. I can see Aaron shaking his head, because like if you actually get into it, it is actually hard. You'll figure out that if you have some classical, you have knowledge of the classical algorithms, it becomes easier to do reinforcement learning. If you don't, it gets really hard. As I said, reward shaping is extremely hard, right? So basically what it means is like in reinforcement learning, you have to set a function that says that, okay, whether whatever you did is successful or not. And so that's the feedback you give to the system so that it can continue doing the same thing over and over again, so that it would maximize the reward or tend to go towards the desired behavior you want to get. But it sounds really easy on when I say it in English, but you have to do that mathematically, right? You have to say that, okay, what is this mathematical function that I can give that will make it do what I want to do in English? Like, let's say this robot has to pick something and place it somewhere else. It has to avoid this trajectory, or it has to do it this fast and things like that. So how do you do that in like specify it in a mathematical sense? And that gets really hard. So if you have like classical background, then it becomes a little easier, because you know like what are the things that are shaping it, and then you can kind of like use that knowledge as well. But the holy grail of this deep learning and everything is like, okay, you just throw some data at the system just learns what you want to do, including all these rewards and everything, and then does what you want to do. So that's kind of the holy grail of like all these learning models. I like 5 years ago, that was just a dream. Like there was no hope that something like that could happen. I think now things are changing a little bit. I'm not saying it's there yet, but things are changing quite fast and progressing towards that. So this is called like general level intelligence, right? So things are getting there, but it's still a long way from that. Like it'll eventually, maybe in 10 years we'll get there, but still it's not there yet. Okay, questions.
What do you think about the figure humanoid, sir? How do you think it's
Figure?
going to be applied in
Uh,
the real world?
like just the figure humanoid, or like humanoids in general?
No, figure, especially because of the way that they've been marketing themselves as a household-based humanoid.
Yeah. Okay, so I think, well, I'm not a humanoid expert. I'll start with that. But so I can give you like my general opinion on that. So it's kind of funny that figure is, I don't know if you guys have seen this. Let me check. So this is the humanoid that Arvind is talking about. They kind of like publicize that you can have this robot like at home and do like regular household chores. And that is kind of like, and I have mixed opinions on that. Like the first thing is we're not there yet. There's like what figure can do is kind of um, it's still a gimmick at this point. There is still a lot of problems to be solved before you can have like a humanoid robot that you can have in your house to do this household chores. So um, so that's kind of like the bottom line. So what I'm thinking about that is like, if you have a robot like um, these robots that clean your floor, whatever it's called, the vacuuming robots.
Roombas.
Rombas, yeah. So Rombas, I mean, even like, okay, so Rombas are the ones which actually became the first kind of robots that was useful at home, right? And even that took a lot of years to actually get in people's homes. Um, but if you look at it, it's one of the main things that they focused on and kind of made or kind of made sure that it works really well is the utility. Like whatever it was doing, they just made it so robust that it can work in anyone's place, and people would kind of forget that there is a robot doing that thing in the background. So that's kind of like the end goal need to be. If you have a robot that is like you need to babysit all the time, it's not going to happen. Right. So that is where I see figure right now. It is at a stage where it needs a lot of babysitting. Right.
I
Like,
heard on the figure,
uh-huh.
initially Microsoft supported all the code and everything,
Mm-hmm. Mm-hmm.
in their levels, like they gave them
Mm-hmm.
level 3 code, and
Mm-hmm.
Figure was trying to now develop everything in-house, and they don't have right people, or they're struggling. To your
Mm-hmm.
point, it's more of a gimmick, or
Mm-hmm.
they're still like work in progress, let me put that way,
Yeah.
not just
Yeah.
outright it.
Yeah.
It's close by. They had here in BMW factory. It's like 30 miles from my home.
Mm-hmm. Mm-hmm.
The Figure robots, no lot of people. It
Mm-hmm.
was very confined space. It worked, and
Mm-hmm.
BMW kind of has mixed opinion on having the sheet metal area, because the
Mm-hmm.
current like sheet metal handling is very simple. If you
Mm-hmm.
see in terms of robotic point of view, it's pretty what do you call nothing novel at this point, handling sheet
Mm-hmm.
metal
Mm-hmm.
in the shop. So
Mm-hmm.
it's it's kind of mixed opinion, like
Mm-hmm.
more dexterity task, like handling plastic or
Mm-hmm.
tubing or something of that kind. It's
Mm-hmm.
still not there. It were
Mm-hmm.
handling flat surfaces, or I mean curved surfaces. So
Mm-hmm.
that was from like people I know or close
Mm-hmm.
by, they were saying.
Yeah. Yeah, I think that's so I yeah, I think one of the main things that I think is important for any humanoid robot to succeed is the dexterity of its hand, right? So when you think about a humanoid, the first thing is, oh yeah, it looks like a human, does things like a human. But what really matters is not how it walks or how it hops or anything like that. What really matters is how it handles things, because humans are really good at that, right? Like our dexterity of our hands is mind-blowing. We cannot, like, if you look into it and if you try to replicate it in a robot, that's when you realize that, oh my God, our hands are so dexterous and can handle really complex things in such a high level of accuracy that getting a robot to do that is kind of impossible. And one of the main reasons is because we spent several million years honing those skills, like as primates, that we kind of discount that, right? Like we develop these skills to um, manipulate things, like before we even develop the math skills, right? Like all the prefrontal cortex is the one which is responsible for all the math skills and all these complex kind of thinking that we have. But that just came in the past couple of decades. The past couple of thousands of years. But then the manipulation skills that came like several million years ago. So we kind of we kind of take it for granted, we discount that. But when that comes to robotics, that's what people are struggling with, and that's where they don't have the data to. So there are some efforts to kind of like get the data there, to have these deep learning methods to deal with it. But unless we get some robots that are capable of having that level of dexterity and usefulness with the arm, um, these robots are not going to be in the homes any soon. And figure, the more I see it, it's like, okay, it's looking more like a gimmick. And I think one thing that they did is like they put a cloth surface on top of the robot to make it look more like human. And I think it's just like a psychological trick, right? Like if you see a robot wearing cloth, it feels a little closer to to a human. It's not like something intentionally we think, but that's how like the psychology works, right? So that's that kind of a gimmick that they did and kind of helped them to a certain extent. But now, like, okay, now you have to prove things in the real world. They are not there. And for that matter, I don't think any robotic company is there. And as Sumant was mentioning, like it's pretty hard to keep robotic companies afloat. Over the past decade or so, there's been a lot of companies that showed a lot of promise, but then when they came to the to the market, they could not survive and they just went out of business. There is a lot of robotic companies in the market space. So, but things are changing now. Like there is a lot of robotic funding that's flowing in this year specifically. So hopefully these two companies would survive, but we'll have to see. It's a hard business because hardware based business is really hard to kind of grow and sustain. So that's one of the main reasons, and also like finding the application, right? So we do have the application. Either you have to prove that this robot is the best for that application, which is kind of like a hard thing. You have to have like really advanced algorithms and setup and everything to kind of prove that. We are not there yet. Or there should be an obvious application. Like for example, if you're trying to vacuum your house, you know that is an obvious application. So if you have a robot that can do that, then it makes sense to apply the robot there. But for a human eye, there is no such a obvious application like that. So that's where people are really struggling. These robotic companies are struggling. But as I said, like the funding situation is changing now. So hopefully in the next couple of years, maybe these companies would succeed. And also the focus from AI-based technologies to, okay, something that is embodied AI, which is robotics. People are making that shift now. Like they realize that, okay, a really smart chatbot is okay, but it can only do certain things. How do you get that to real world? Like how do you make a robot do certain things that are in the real world? And and robotics is the obvious solution for that. So people are kind of tending to move into that realm now. Okay.
So one really impressive thing that I observed in all of these robots is the battery life that they advertise. So I was working on a full-scale humanoid recently. I was calculating the amount of current that the motors would actually require. So even for a lower body application, which I was calculating for, there was a constant current of something around 150 amperes, and
150 amps.
at
Wow.
48 volts.
Oh my God. That's a lot. Okay. So this is like just
And
exerting, like just walking around, or like what kind of activity are we talking about?
so those motors were actually rated for a peerage of around 40, 50 amperes, and we had 10 of those motors. And when we tested them for normal walking application, we saw about 100 to 120 amps. And when it became a little bit more stressed, it went to those current ranges. And
So are these like peak currents, or these like sustained currents, like 140 amps, like a
sustained
sustained?
currents were around 100 to 120 amps.
I see. Wow, that's a lot. Like I'm just calculating that, and so 120
Yes.
amps at 48 volts is like 5,760, like close to 6,000 watts.
Yes.
That's a lot of
And
power.
I was surprised to see that these people are like advertising on more than 4 hours of battery life or things like that,
Yeah.
when I could not even see practical battery life of more than half an hour in my use case.
Yeah, yeah. I think that's kind of like a big deal. So just out of curiosity, like what kind of wires that they use? I mean, like at like 100 amps, I think you should be like pretty close to like Arvind, you're muted.
Oh, okay. So we were looking at 8 AWG wires for a certain purpose, but for the individual motor wiring, we were looking for 12 AWG.
12, okay.
And
Yeah, 12 can still handle maybe 10 amps, like 20 amps, right? Something like that.
so each individual motor would have a rated current of maximum, say something like 30 amps. So
30 amps,
we were
okay.
seeing that copper 12 AWG was able to handle that much. Whereas
Yeah.
the battery wires themselves from the battery had something like 8 AWG.
Yeah.
So
Yeah.
it was limited there. We couldn't do
Yeah,
much.
so for people not knowing that, 8 will be like really thick copper wire, like even hard to bend. Uh, so it's just kind of like what he's talking about. So the connectors that goes in will be huge, and there's like once you have that much current flowing, there's a whole bunch of things that you need to change in your circuitry. So one solution that generally people do in these kind of robots is, if you have so much current flowing in, you kind of like switch to a higher voltage. Like let's say instead of 48, if you switch to like 72 or something like that, then the amount of current would go down. So you can now use thinner wires, not so thin, but a little bit thinner. So that's something that they do, and we recently built a robot, um, and we had to like, considering the current, we switched to like a 72-volt supply. So even then we are getting like 10 amps of peak current in the motors, and so we did use like a 12 gauge wire for that. So yeah, so I mean, the other part of the equation is like the C rating of your battery, right? Like that will tell you like how much power, like let's say your battery has a capacity of 5,000 watts, watt hours, and then it's the C rating says how much of that power rating, or how much of the current that you can draw from the battery at any particular point of time. And so you cannot use any regular battery, because if you use a regular battery which has a low C rating and pull a lot of power, that is a fire hazard, because it'll heat up the battery, and then you can even blow up the battery. So it's a lot of changes there. So I'm really surprised at how they, like, have you guys heard about the robot marathon that they did in China a couple of months ago? So
Yeah.
yeah, so I don't know how they even did that, right? Because like with the amount of currents that Arvind is talking about, it's kind of like it's a big deal. Maybe that's the reason why it was a big deal, right? Like you don't have that level of technology at this point. And I'm pretty sure that Marathon actually pushed the technology uh, further ahead because people have started to think about those things.
I
I
have
know
a
the one. Sorry, go
sorry.
ahead.
Oh, I have a meeting this coming like 10 days from
Mhm.
now with
Mhm.
Apptronic.
Mhm.
They were trying to see if they can use their robot for industrial application, or they wanted
Mhm.
to see what like how to collaborate. So I'll
Mhm.
share with you how that
Sure.
goes, like
Yeah.
what they have in case if
Mhm.
I get to see.
Sure. Yeah. Yeah, so it's kind of like really hard. I think like one thing I read about these marathons were like none of them completed in one battery, which is not surprising. And I think the one which succeeded or like the took the first place, I think they had like 3 or 4 battery changes during the run, which is still impressive. And I don't know how much of a big battery that was. Yeah,
And when
cool.
it goes to that marathon length, we also have to calculate the amount of stress and the temperature change that the motor goes through.
Oh yeah, that's true. It is funny that these robots, a lot of these robots did have sneakers like shoes that humans wear, things like that, because their legs are like they're not set up for like regular asphalt roads or something like that. So they ended up wearing these shoes for humans. Cool. So I think we talked about the humanoids and things. Sumant, you mentioned about Git, so maybe we can briefly touch upon that. And
Sure.
uh,
Um,
okay, cool. So I guess I don't know how many of you are familiar with Git. Probably Arvind, you're familiar with that.
I'm sorry,
Feel
I
free to.
really did not get the term. Can you repeat that?
Oh, Git, the version management system.
Yeah.
Yeah. So if you worked with some code, you're probably familiar with Git. So I can give you on a high level what it is, and then someone you can ask specific questions. Okay.
sure.
So on a high level, this is something that is doing version control, which means that you write some code, you kind of check it in the sense that you record that, okay, this is a change, and then you keep doing that over and over again. And with code, what you realize is, oh, I want to know what I wrote like maybe a couple of changes ago or like a couple of days ago. Then you can go back and look at the change and say, okay, this is the change I want to try, and then you can branch off of that. It also becomes a lot more, or basically the more useful use of it is when you have multiple people working on the same code base. Then you can kind of version control, saying that, okay, this person checked on this code this date, I'm checking in this code, and then you can say, okay, there is a conflict between these two pieces of code because both of them worked on the same piece. Then you can resolve those conflicts and check it in. So there is always a single piece of truth that you're kind of holding on, and then you also know like where it all started and how things evolved going forward. So that's kind of like the on a high level what a version control setup is. The funny part is once you start using version control um, and kind of see the benefits with it, you start thinking like, okay, why do other things don't have version control? Like, let's say you're writing something and you will think like, okay, it'll be nice if I can version control that because I wanted to go back like maybe 20 minutes ago on what I wrote and then get that back. Or you might think about like if you're designing things, you went like, okay, how can I get the version control? Like how can I go back? So the undo and redo things that you have on softwares, that is, you could think of it as like a really trivial, naive implementation of version control, though it's not mentioned that way, but you could think of it that way, where you can go back and forth a couple of changes. Um, but yeah, so that's about it. That's about the version control part. And what Git specifically is in the past, there used to be like um, I mean, in the past, like let's say maybe 20 years ago to 15 years ago, version control was not like what we have right now. What generally happened was you have a central server where it has records all the code and all the history. And basically, when you want to check in a change, you will make the change in your local computer and you'll push the change to the central computer. The central computer is the one which generally keeps all the changes. So the local copy that you have will not have all the history. It'll just have maybe whatever commit changes that you had, and that's about it. And this all changed when Git came into the picture, where they said that, okay, every repository is a full repository on its own. The sense that every repository has the whole history. So there is no longer one central server that is holding everything. All of our repositories will hold everything. So everything is a server now. So it's basically decentralizing the concept, made possible because storage became cheaper and network became cheaper and everything. So
I see.
um,
Okay.
so that's when Git came into picture. So I think people starting with Git, they don't really understand that, oh, it was like this before. Like it seems obvious that you have to all the repositories should have history, because if not, it looks like it's something incomplete. But that's how things were like a couple of years ago when I
Okay.
started. That's how things were. So that's kind of like the big picture, right? Okay, where things came from and where we are right now. So as far as the commands itself are concerned, there are just a handful of commands that you need to know. Like one command I use the most frequent is called git status, which just tells you which branch you are in. Are there any files that you have changed in the current branch? Are those files staged? Are there any untracked files in there? So that's what it shows. So let me just break down what all the things I said. So I said what branch you are in. So a branch is basically, you could say that, okay, when you use Git, you have one main branch where all of the codes are progressing. So you could think of it as like one linear progression. But then you can also branch off of a particular change and make changes separately. It's basically like trying out something different. And then when you like that, you can merge it back to the main branch, or when you don't like it, you can get rid of it. So that's what branching is. So it tells you which branch you are in. And then we have something called files that are staged and non-staged. So what that means is when you have files being tracked in Git, and when you change a particular file that is being tracked, then when you make changes to that file that's being tracked, you see that, okay, this file is being tracked. And you have to explicitly tell Git that, okay, I am ready to commit this change. So you basically say that, okay, this change in this file is what I want to commit. So you're basically staging the change for a commit. So that's what staging is. If you're telling Git that I want to commit this change. So that's what staging is. And then untracked files is like if you create a file which is not being tracked by Git yet, then it'll show up as untracked files. So there might be some files that you want to keep in a repository that you don't want to check in or don't want to do version control. So those could be there. Or if you added a new file after your Git repository was created, and now you want to, you haven't added it into the repository yet. So now that will be an untracked file. So you can basically stage that, and once you stage that, then it gets getting started or gets tracked, and then you commit it. Now it's being tracked, and that's kind of like how we do it. Okay,
Okay.
Jishnu,
Yeah.
thanks for pointing to that. Yeah, I've used this. This is really good, cool.
Oh.
Yeah, so go through the link that Jishnu shared.
Yeah.
So I think I mean, so I guess like I said a couple of commands, right? Git status, git add, git commit, git checkout. That's pretty much like just 4 commands I said, right? That's pretty much what you need initially to kind of get yourself familiarized with. And once you understand that, then you can add more commands to your understanding going forward.
Got it. Okay.
Okay.
Thank you. Thank you, guys. Yeah.
Sure. No problem. Okay. We're on time.
Last thing.
Sure, go ahead.
On the terminal log.
Mhm.
When in the group chat or whatever I post, like people ask for terminal log. How do I look at it, or I have no clue on that?
Yeah, so
if
terminal
somebody
log is
says. Mhm.
yeah, terminal log is something that you see in your terminal or your console or like command prompt or like wherever you're typing things, right? Whatever text that gets dumped there, it's called terminal log.
I see. Okay.
So you just copy that and then paste it into this thing. That's good enough.
Okay. Makes sense.
Okay.
Yeah. Mhm.
Okay.
All right.
Cool. Anything else?
Not at the moment, but thank you.
Okay. Sure. Okay. I guess we are at time. So let's close this meeting now. Thanks for joining, guys. We'll talk to you next week. So if you have any questions or if you want to have any discussion points, bring it to the meeting and then we can discuss that. Okay.
Okay. Thank you. See you guys.
Cool.
Yeah.
Sure. See you then.
See you guys.
Thanks for
Bye.
the
Bye.
time.
Mhm.
Bye bye.
Bye.